Hello everybody and good morning. I am Mohammad Zaganabati and today I'm presenting our empirical study on resource and memory leaks and their repairs, which was published in EMZ last year. This was a collaborative work including 4 members of Heidelberg University and David Lowe from Singapore Management University at the time of the publication. And of course, in this very little time, I cannot go through all detail of the work, so I highly encourage you to look at the work in the journal website. A questionnaire with Microsoft engineers showed that the leak detection is still one of the top challenges for the software developers. But why this is still a top challenge even with having in mind that so many works are already published in leak detection? One approach is to look at the bug repositories and try to get more information and insight about the problems facing the developers with answering questions such as how are the leaks detected, how many files are modified to fix a bug, and are there any common patterns in leak detection fixing leak-related bugs. The result may help us to find the gaps and also can be a guidance for future research and diagnosis of leak-related bugs. We also realized that there are not so many comprehensive studies on leak-related bugs which can answer all of the open questions. Therefore, to fill this gap, we conducted an empirical study on leak-related bugs and their repairs. And as you know, for a valid empirical study, we need first to have a proper methodology. For this work, we selected 15 projects from 2 most popular repositories for Java projects, Apache and GitHub. Then we search for the issues which have 3 criteria. It should contain the keyword leak, it should be a bug, and it should be already fixed. It's worth mentioning that we only consider reported bugs and not those bugs which are already fixed during code development. Then, for each issue, we collected summaries, descriptions, comments, patches, as well as timestamp. We used this data to answer the questions. And the first question, we wanted to find out how are the leaks detected by the users. We found 2 main methods, source code analysis and runtime analysis. As you can see, the runtime detection was more common and more resource leaks than memory leaks were detected by source code analysis. We also found 2 other interesting results. First, in about 11% of the cases, a failing test caused a leak to be detected by issue reported, and only in 1 case, the leak was reported by a static analyzer. It is possible that already developers use the static analyzers during code development and fix bugs who could be found by static analyzers already. Therefore, this result shows that the runtime detection is still the dominant detection type. We also analyzed the root causes of the leak-related bugs. We found that about 80% of the leaks were caused by 4 major root causes shown in the red box. Interestingly, we found that in about 76% of the leaks, they were manifested in normal execution path, and this is the execution path in absence of exceptions. We further analyzed the patches to see if there are any common patterns in fixing leak-related bugs, and we found that 13 recurring code transformations, which fix about 57% of the issues in our dataset. Here you can see an example of a memory leak issue in which developer changed a variable from a static to non-static to fix the bug. We found 4 cases which have the same pattern. This shows that it's possible to extract repair patterns from bug fix history. We further analyzed the bug fixes to find how many files were modified in order to fix leak-related bugs. And we found that in about 54% of the cases, only 1 file was modified, and only in 12% of the cases, 3 or more files were changed. This result shows the high locality of fixing leak-related bugs. Finally, to conclude my talk, let us summarize some key points which we have learned from this study. By analyzing the bug history, we can find some good practices to avoid recurring leaks. We found that in some cases the user detected leaks via failing test. This can motivate automated test generation for leak detection. Our study also showed that the fixes of leak-related bugs are highly localized, which is an interesting result for automated program repair. And last not the least, we found that there are common patterns in fixing of leak-related bugs, so template-driven patch generation can be one way of fixing such bugs. Thank you for your attention. I'm looking forward to your questions via Twitter, Gmail, and now.